the clerk will engage in a silent roll call while the members review the minutes of the January 11, 2022 meeting. Has everyone reviewed the minutes of the January 11, 2022 meeting? Are there any additions or corrections to the minutes? It appears we have a quorum from the Senate, but not the House at the, we do have a quorum. All those in favor of approving, or I should say, call upon the co-chairman for a motion.
Mr. Chairman, I move to approve the minutes from the January 11, 2022 meeting.
You've heard the gentleman's motion to approve the minutes of the January 11, 2022 meeting. All those in favor of the motion will signify by saying aye.
Aye.
All those opposed will say nay. It appears the ayes have it. The ayes do have it. The motion is adopted. Just a little bit of housekeeping. Of course, I want to thank WVU and Morgantown for hosting our interims. This session is very exciting to be here, especially in lovely late spring. It's a beautiful drive this morning. I hope all of you enjoyed it. This is not our normal meeting room, so these microphones do not work the way that ours work, where you push a button. Now that we are live and this meeting is going, these microphones will pick up everything you say. So if you do need to have a conversation or, look at a message or talk to somebody, please step away from the table. Nobody will be upset with you. We do have one item on the agenda today. We have personnel from Westinghouse, and I'll allow them to introduce themselves as they come up. I believe we have 2 or 3 different presenters from Westinghouse. Westinghouse Nuclear's presentation on nuclear power in the Evinci microreactor. I believe Mr. Yost, Chip Yost from Westinghouse will be our first presenter.
Actually, Mike Moore coming in.
Mike Moore will be our first presenter. If you go ahead and come to the podium, and do we have you set up with, I believe you had a PowerPoint. It's up there? Okay.
All right, shall I begin? All right, so I'm Mike Fallour from Westinghouse Electric. Thank you for hosting this and letting us be here today to talk about the Evinci microreactor and a little bit about nuclear in general. But I'm the Senior Director for Advanced Reactor Commercialization with Westinghouse. I've been with the company a little over a dozen years. I spent almost all of that time on execution of our AP1000 projects in China and the United States. Prior to taking this role for really driving our new technologies into the marketplace, I led North American supply chain for Westinghouse. I was responsible for delivering all the equipment and the materials to the large nuclear construction sites in China and the United States. Prior to that, I worked in supercritical fossil. So I'm very also experienced on the fossil side of energy generation as well. A little bit about Westinghouse. Westinghouse is not the massive conglomerate of old, making televisions and washing machines and all those types of things. That company was substantially broken up by CBS, the broadcasting company, in the 90s. But the nuclear division stayed intact from that breakup. So Westinghouse Electric is still the nuclear company that really, and the energy company that draws its lineage back to even the 1800s. And Westinghouse has put nuclear technologies all over the world, including the first commercial power reactor in the United States at Shippingport, right outside of Pittsburgh, where I'm from, as well as the first naval submarine reactor on the USS Nautilus. From there, we have commercialized nuclear technologies, delivered them all over the world. The Korean nuclear fleet, for instance, is completely Westinghouse technology. The French nuclear fleet is also 100% Westinghouse technology. We actually built the entire French nuclear industry, so we have the experience, and one of the things we'll talk about is really the interest of helping to support, expansion of nuclear capabilities within the state. And we can certainly do that in the state as we have done it internationally and actually created entire nuclear industries for some of the major nuclear using countries today. A little bit about advanced nuclear. So just in general, there's a lot of discussion about advanced nuclear in the United States and even globally. It's become, quite an exciting time to be in this field. And there's really, the way to look at these types of plants is there's the large conventional plants, which are like the pressurized and boiling water reactors, think 600 to, even 15 or 1600 megawatts of electricity of plants throughout the United States as well as the world. Those are really those large conventional nuclear plants. In between, there's a kind of a new term that's been created called small modular reactor. And those are really somewhat medium-sized plants, perhaps in the ranges of 300 or maybe even a little bit more than 300 megawatts of electricity. But really what I'll focus on today, even though I'll mention our AP1000, is far at the small end of the spectrum, called microreactors. And microreactors are really less than 10 megawatts of electricity capable. So similar to the size and the capability of many of the research reactors throughout universities, throughout the United States and the world today. But also the potential of microreactors offers some interesting, potential benefits, outside of just a pure research application perspective. But really microreactors, they have an extremely small physical footprint. They're a much smaller capital investment, obviously, perhaps, than a very large conventional nuclear power plant. They're transportable and they're also scalable. So you can add these units, you can take them away, and I'll talk a little bit about how we do that. And they're also very safe. They're also water-free. So the eVinci that I'll talk about, the Westinghouse technology, it doesn't require any interaction with water. The only interaction with the environment is actually air going into the power conversion system and air going out, with no irradiation or anything associated with both that air going in and coming out. And then really from a microreactor perspective and our vision of what could potentially be done in West Virginia is really to take advantage of the versatility of this type of technology by utilizing it as a research type reactor, something of which the state could test all sorts of different applications such as hydrogen generation and other things with a technology that can put out both electricity and a very high amount of heat. And I'll talk a little bit about that. But first, just a moment on our AP1000. So this is the Vogel site in Georgia, right outside of Augusta. For, again, the 6 years prior to this role, I was responsible for delivering almost everything you can see on this site. And this has been a difficult construction. I spent many waking nights working on this project. The U.S. nuclear industry had to substantially be rebuilt by the execution of this project. People ask, why has this been slow? Why has it been difficult? Why is nuclear hard? We hadn't done it for about 40 years as a country. So it was really a gargantuan effort to both rebuild the supply chain in the United States to be able to do a construction site like this while we were doing it. Those things it was very difficult. But what now we can capitalize upon is this type of technology, as well as what we did with the nuclear supply chain in the U.S., is really build up that human capital, as well as the technological capability to be able to do these projects again. This is the only design, and again, I'll talk more about our microreactor, but the AP1000 design, it's the only nuclear plant right now that's been licensed recently that's really a shovel-ready project as well. So, there was a study that was just put out by MIT that basically confirmed that the price of this construction will be dramatically reduced for the next units. And I can say, with complete certainty that many of the first-of-a-kind, really all the first-of-a-kind issues we dealt with, they were resolved on this plant, on this Vogel plant. And now the construction labor, as well as the U.S. supply chain, is really ready now and capable to do projects like this again, which can't be understated how important that is strategically for the United States. For our microreactor, much smaller than that big AP1000 plant. So AP1000, more of the conventional nuclear. This, again, extremely on the other end of the spectrum of extremely small size nuclear plant. This unit is capable of generating just a little bit over 5 megawatts of electricity, and we can also capture about 8 megawatts of thermal energy at 350 degrees Fahrenheit simultaneously with that power generation. We also can operate this device in a heat-only mode, where we can get about 13.5 megawatts of thermal energy out of it at temperatures over 1,300 degrees Fahrenheit. And those two different modes of operation support a wealth of opportunities to do research in many of the different energy fields where, high temperature heat as well as electricity is necessary to move really the United States forward. Hydrogen, for instance, is an extremely popular topic right now, but you either need electricity or you need very high temperatures to generate hydrogen efficiently. There are things that still need to be proven in that space, and this type of technology could really support the research and development in just that field, to name one, of which there are actually many. This design is actually truly transportable. So in this term of small modular reactor, it's actually a very widely used term now, but I can assure you that this design was made to be transported to extremely remote areas, because that's one of the early applications we see for this technology, is to be able to substantially support replacement of extremely high-cost diesel energy in remote areas like Alaska and Canada. There are people in Alaska, believe it or not, who their electricity bills are over $1 per kilowatt hour. So, pushing 5 to 10 times what any person in this room is actually paying for electricity today, let alone some of the industrial opportunities in remote areas such as Alaska from a mining or other industrial perspective that cannot be economically commercialized because the cost of electricity in some of those areas is just too high. We've done a lot of work on this technology to ensure that it will be cost competitive. We released some studies on this last year where we know that we can enter the market in this area of high-cost diesel very successfully. And our vision for this technology is to basically build them like automobiles at some point in the future and really drive that electricity cost where it could even challenge some areas of the grid from a cost efficiency perspective. From an operational perspective, and I'll talk a little about this, there's really almost nothing to operate. So in the large power plant, there are many seasoned operators. They go through long qualifications to be able to operate a nuclear power plant safely. One of the advantages of the Westinghouse design in this microreactor space is there really isn't anything to actually physically control. So from a controls and a safety perspective, we really just don't need this large number of operators that's typically used for a large nuclear power plant. Again, we actually see this very much like U.S. research reactors, where they're typically actually operated by grad students, which is not something that's well known, but that's being done at universities all throughout the United States today. And what we're most proud of perhaps about this technology is, there's a lot of people in this space that are talking about advanced nuclear, but a lot of them continue to just talk about it. And what we have done is really spend the last 4.5 years actually building and testing components of this design to make sure that we're ready to bring it to the marketplace and potentially bring it to a place like West Virginia or West Virginia University successfully. The photo in the upper left is actually it's an electrical demonstration unit that we built right outside of Pittsburgh at our testing facility called Waltz Mill, where we do a lot of field services work throughout for plants all over the United States, but also our eVinci research and development facility is also there. But really, kind of another way to think about this is it's very much like a battery that's charged with uranium. That uranium the energy in that uranium is discharged by making heat. And you can take that heat and either use it as heat, or you can convert it into electricity, or both. And another way to think about this, even from a size and a deployment model perspective, is it's very much like a diesel generator. And Westinghouse did that on purpose because that's one of the key markets we see over the long term for this technology. This is the actual reactor canister itself, and I won't get extremely deep into how the technology works. But there are a few key differences of this type of design versus really any operating nuclear plant today, and really different from some of the advanced reactors that are being talked about. This design does not have a high-pressure pumped coolant system, which is a key difference, right? When we talk about safety in nuclear, nuclear plants in the United States operate extremely safely today. We haven't had really an accident since 3 Mile Island, and 3 Mile Island was a much smaller accident by far than Fukushima, and much smaller even still than Chernobyl. But those plants, they must maintain water pumping through that core to keep it cool. Otherwise, that is what happens when you get a nuclear meltdown. So if you lose the ability to pump that fluid, you lose the ability, or the fluid leaks out, the fuel in those types of plants will melt. So that is why there is so much work done to ensure that you can always keep water coursing through the reactor core of large plants. And we've done that extremely successfully in the United States. So I do want to say those plants are very safe by design. But what's different about this design is there's actually no pressured cooling system in this design at all. We are using hundreds of heat pipes, which you can kind of see the stainless steel looking metal lines at the top. Those heat pipes are actually subatmospheric pressure, and they completely passively transfer heat from the nuclear fuel. So we don't need a high pressure gas or a high pressure water system. And that being slightly subatmospheric, you know, the cooling medium, which is sodium in these pipes, does not want to try to burst these pipes. So it's a low pressure, passive heat transfer machine. That elimination of that pump system also allows us to have a very simple machine. So we don't have pumps, we don't have a huge amount of piping that's typically associated with the nuclear power plant. We don't have all sorts of valves that an operator needs to know how to adjust to properly operate it. Basically, this machine is going to constantly be pulling heat away from that fuel, almost no matter what someone does with it. From a safety perspective, that's a very nice advantage. Also, the fuel we're using in this reactor is called TRISO. It is, and this is the US DOE has been developing this fuel for about 40 years. And the US DOE has said it's the most robust fuel form on Earth. And US DOE, and I use their words because I think it adds credibility, US DOE has also said it's a meltdown-proof fuel. And the way that's accomplished is a very tiny kernels of uranium that are coated in materials that can withstand the highest temperatures that uranium could achieve. So between the low pressure, basically subatmospheric pressure cooling of this design, as well as utilizing the most advanced nuclear fuel that's been developed to date, we really have a machine that does not require, large numbers of operators, and it's also extremely safe. Very safe compared to, other, again, research reactors that are operating in populated campuses all throughout the United States and have been safely since the 50s. Another interesting feature of this design is when it's sitting at just a normal full power operation, there are actually no mechanical moving parts inside the reactor system at all. It's literally only the heat that's moving through these heat pipes, which is happening naturally, and all the rest of the pieces are just fixed. So extremely simple, extremely safe by design. Here's a little bit more just about the fuel, so you can kind of see on the left, that's a magnified view of this TRISO fuel form, and that sphere in the middle is the uranium. But then you can see that in the cutaway, there's multiple other layers of material on top of that piece of uranium. And again, what those layers do is prevent, even if something would happen where the typical controls are not working, that kernel of uranium cannot achieve a temperature or a pressure which will break those outer layers, hence the meltdown-proof fuel. From a pressure perspective, again, there's no pressures in this system that are trying to break. Imagine in your house if you have a leak in your faucet or your piping, right? It's really the pressure in that pipe that's causing that water to want to come out. And that's why, everyone here, I'm sure, has dealt with some sort of leak in their house or their, even in their cars for different things. It's that pressure that's really driving that fluid out. We don't have that in this design. And then from a typical controls perspective, we have two ways to be able to control and shut down this reactor. And even if either of those two ways, two systems do not work, again, we can maintain the reactor at safe temperatures and obviously prevent any potential release of radiated material. A bit about our deployment model. So this plant, again, when we talk small and modular, I would say this is the most small and the most modular of all the designs being talked about today. We deliver the entire system in 4 containers. Basically, oversized truckload size container for the reactor, one for the power conversion turbines, one for the instrument controls, and then one other cabinet or container for different ancillary equipment that are really just needed to support what we're installing this unit to do. But this allows us to move this design to wherever we believe we would need it. It allows us to scale them so we can add units, we can take them away. But perhaps most importantly with our design, it solves a key social challenge that has somewhat stifled the ability to expand nuclear power throughout the United States, and that is the storage of spent fuel and waste on the site of operation. So all of the large nuclear power plants today, because we do not have a deep geological repository such as Yucca Mountain, they all must keep their fuel on the site. This design, we bring the reactor with the fuel in it after the fuel has been expended, which is at least 8 years of full power operation. We actually take the entire reactor away back to a licensed facility where we would remove the fuel. So if we would install a reactor like this at West Virginia University or another location in West Virginia, you are not saddled with having to deal with the spent fuel within the state. It's a huge difference of this design, and it was a key tenet of why we worked so hard to choose a design and features of a design that could be transportable, is really to solve that social challenge. And then purely from a decommissioning perspective, decommissioning a nuclear plant is typically not a simple task, as you could probably imagine. With this design, once you've removed the reactor, you're really left with a diesel generator type building to deconstruct if you want to turn the site back to a green field. This facility is, again, right outside of Pittsburgh, Pennsylvania, about 40 minutes southeast of the city. And it's a really quite rural area, but it's been a central piece of the nuclear industry since the 50s. And it's because Westinghouse really developed that first commercial nuclear plant right outside of Pittsburgh. Westinghouse, back into the 1800s, drew some lineage around Pittsburgh. So this facility draws its lineage back to the 60s. And so we've been building upon that. Substantially, the supply chain supports this facility around Pittsburgh, but we're actually also looking at West Virginia suppliers to support this development as well. We utilize several in the state already just because it's so regionally convenient. But one of the things we would like to do, especially if we would work with the university in the future, would be deploy a reactor at the university or another location in the state, and then really build out the infrastructure around nuclear in the state. Westinghouse, again, we've done that across the ocean multiple times. To be able to build a high technology, readiness of suppliers within West Virginia would actually be almost trivial for us. We could be bringing engineers to the state, really getting the state ready to embark upon, supporting these types of technologies in the future. This is our electrical demonstration unit. So when we talk about, what have we done to really make this a reality, we built up a cell of our reactor. We built the heat pipes that, I mentioned are the way that we cool this unit, and we ran this up to its full operating temperatures, and it worked as we had expected it would. It basically physically validated all of our computer analysis, all of those things. And the reason I mention this is, again, we have set the base to actually be able to build this unit. There's a lot of people in advanced nuclear trying to sell their technology, but we didn't even really start talking about our technology until we successfully completed this test last spring. We've taken a very different approach of we need to be sure we can actually deliver something before we would come talk to a group like this today. We really just don't have a lot of interest in marketing something, and then not being able to deliver. Westinghouse will be successful if we deliver these projects and we deliver them on time and for cost. Other pieces, parts, you can actually see this is a heat pipe operating at over 800 degrees Celsius. It's about 1,400 degrees Fahrenheit. We set a record runtime for that heat pipe as part of our development program about 2 years ago. And then there's just other pieces and parts that we have been building and testing and doing all sorts of iterative design to make sure we're optimized for this type of machine. The upper left is a scaled manufacturing demonstration. The upper right, those are prototypic heat pipes that we just had manufactured and delivered to our facility, the raw material just a couple weeks ago. And then you can see that there's graphite for the core. We've built tens of graphite core cells just to make sure we could really zero in on the tolerances and, you know, the way we would make these things. And I don't mention this necessarily because it's, you know, I want you to all understand the technology, but the things you see here can be all manufactured in this region, and certainly in this state with some time and some investment and some support from a company like Westinghouse, and bringing along your flagship university of West Virginia University perhaps in the future with Westinghouse to develop these capabilities. You know, those tubes right there, the process that was used to make those, it's a facility in Blairsville, Pennsylvania. A lot of people wouldn't know that. Blairsville, Pennsylvania is about 50 to 60 miles from Pittsburgh, extremely rural area. We make hundreds of kilometers of zirconium tubing at the highest possible quality you could think of for nuclear plants throughout the entire world at that facility. And there are things like that that Westinghouse has that knowledge, that capability, that we would certainly, you know, be very willing to support, you know, another state in the region right down the road from us to be able to develop capabilities like that. So from a safety perspective, this is truly something that, you know, even if it was operating 100%, everyone walked away, you know, an earthquake, a flood, all those things happen, it's not going to release radiated material into the environment. From a credibility of Westinghouse perspective, you know, hopefully you at least know Westinghouse, but this microreactor technology specifically is the only one that has received funding from both the US DOE as well as the Canadian federal government. So we have grants from both sides of the border because we're interested in deploying this technology in both Canada and the United States. I don't think anyone has done as much physical build and test work as us on an advanced reactor program like this. Would love to host, you know, anyone interested, and we actually have hosted a few of the folks in this room to our facility. It's only about an hour and 10 minutes away, where you can really see all of the parts and pieces of a large nuclear plant physically, and then also be able to see what this eVinci microreactor looks like. So we have kind of a nice advantage at our facility. We have all the things we do for the large nuclear power plants contrasted with our testing center for the very small plant that I'm talking about today. And it really, you know, even if you're not, you know, you think there might be other technologies better than Westinghouse, et cetera, I think just that visit as well can give you really, in just a few hours, you can get a perspective of what nuclear really is. But some of the things for West Virginia for this type of unit, you know, we could really see it supporting the university and the infrastructure for nuclear in West Virginia. You know, I'll be very honest, I don't see thousands of these being deployed into West Virginia, right? You have many other types of energy sources that you can take advantage of, perhaps even, you know, building a large nuclear power plant in the state someday. But a small plant like this that could really support the university to build that nuclear program and then the subsequent supply chain infrastructure around something like that, it's really an accelerator to help put the state in a place that it could support nuclear projects not just in West Virginia, but wherever they are. Right? The nuclear supply chain tends to be a very global supply chain. So once you have the capability, it's things that can be exported to Canada, France, you know, all over Europe, who's extremely now interested in new nuclear, certainly in light of the events in Ukraine. Also, just energy and research centered in West Virginia. You know, a platform like this that you can use to test new hydrogen technologies, test people's industrial processes. We really see, you know, putting one of these at university, really more than one at different universities, because we think there, you know, certainly there's 30 to 40 research reactors in the United States today, and they're very well utilized. But putting one of these in West Virginia, you know, you, as an early adopter, could really bring industry to test their technologies with this type of device. And that's what's so interesting about, from a research perspective, what we can do with this. Medical isotope research can be done with this reactor. Again, different energy research technologies, But even training of operators and, developing that nuclear program, there's just so much potential with this. And then all of that application development supports putting these further into the marketplace. And when you look at what could be done with this reactor, it's really anything that could be, done with heat and electricity. So, one of my roles has been trying to figure out what are all the things you can do with these. And it's almost a limitless potential right now. There's discussion about putting them on commercial marine vessels. There's discussion about putting them certainly in remote areas to reduce electricity costs. But when you look at zero carbon, high temperature heat, there really are no viable options right now other than nuclear. To make high temperature heat in industrial processes, it's substantially, you must burn something today. So, I don't think this type of technology will ever replace, the fossil fuels that we rely upon, to make all of the heat in the United States that we use for industrial processes. But there are areas, again, in, Canada, Alaska, some of these places where just transporting liquid or solid fuels, over large volumes just can't be supported right now. So putting technologies like these into those places could really be strategic for industry, but also the United States. And the last thing I'll mention, the U.S. DoD is quite interested in this as well. The U.S. Air Force is looking to put a microreactor in Alaska, and that's because of the strategic value of a technology like this also for our defense. They're relying on liquid fuel to support our overseas bases and even some of our remote areas, could put us in a not so good situation from a defense perspective in the future. So, just the amount, I just mentioned some of these things because that's the amount of potential application. And really those early university adopters are going to be the ones who are doing the work to figure out how to support all of those different applications. Westinghouse, we focus on developing reactors, but, a university could focus on what do you do with it. From a timeline perspective, this is obviously very high level, but we have about a 20,000 activity schedule supporting our development program over the next 5 years. We are likely going to do our first demonstration of the technology at one of the U.S. national lab sites. So we'll operate it, ensure that it works all the ways we expected it to in its full configuration. And then we would see, we could site a unit in the state of West Virginia by the end of 2028. Sounds like a long time, but in nuclear, that's a very short period of time. And especially, as West Virginia University does not currently have a nuclear program, there's time for that infrastructure to be built, and there's time for that supply chain to be built to really start to make West Virginia a center for technologies like this. So it's something that we feel is, decisions, could certainly be helpful to be made in the near term to support this type of timeline and put West Virginia on that early track. But Westinghouse is certainly ready to support. But I'll also be quite happy to take any questions I'm sure you would have today. But thank you very much for your time and attention.
Senator Caputo.
Thank you, Mr. Chairman. I appreciate that. Mr. Lord, thank you so much for coming, and that was a great presentation. I probably learned more about nuclear in the last 20 minutes than I knew in my whole life. A couple questions that I have. Did I hear you say that you won't have to deal with the waste for 8 years? Is that what I heard you say?
Yes, the unit a charge of fuel will last at least 8 years. That's 8 years, 24/7 operation, 365.
Then where does the waste go in 8 years?
Yeah, so Westinghouse will license a facility, and we are looking at different locations for that. Could be an existing Westinghouse facility, could be an existing nuclear power plant, could be a brownfield industrial site, but this is something Westinghouse does. It does not have to be in the state of West Virginia.
What do you do with it when you get it to that location?
Remove it and store it in a cask, the same way as other nuclear fuel has been safely stored for decades in the United States.
Stored underground?
Above ground.
Above ground in a what? What did you say?
In a cask.
What's a cask?
A very thick stainless steel vessel that is made to store fuel for almost geologic periods of time.
Okay, and is there considerations or need for extra security around these type of facilities because of, homeland security issues and concerns?
Yeah, great question. We draw this similar, and this is something we're working with the U.S. NRC on right now, but again, from a size comparison and operational perspective, this machine is very similar to existing U.S. research reactors, which substantially rely upon local campus police response for security. The ability to actually tamper with or damage this device, it would take an extraordinary amount of time, which allows for certainly in an area like West Virginia, to have very adequate security response.
Well, what about like an attack on it? Would that be a concern, or what would happen if something like that happened?
Yeah, so certainly attack is a very broad term, and I'll bring up, because I was asked this question in Alaska, what happens if Russia invades and they would,
Drop a bomb.
Yeah, drop a bomb on this.
Yeah.
That would probably destroy the unit, yes.
Then what's the health risk if that happens?
Again, those kernels will maintain that, yes, they could end up spread around in the worst case scenario of literally a bomb attack, but in a place like West Virginia, adequate response, there's really no way that the fuel or the reactor could be compromised. Typical security regime around a big reactor, you have to prevent a bad actor from getting to the control room of a big plant, because they can press the buttons and do all the things and make it destroy itself. This design, the controls will substantially be a laptop that allows you to turn it on or turn it off. There's not the types of things to manipulate to be able to actually create damage to the machine.
And thank you very much. I appreciate that. Mr. Chairman, thank you.
The co-chairman.
Thank you, Mr. Chairman. Have you heard of recycling nuclear waste that can recycle up to 90%? And if so, what's your thoughts on that?
Certainly recycling of fuel is technically viable, and it's been done in other countries. It's certainly not being done in the United States today. I personally would be an advocate of the U.S. government supporting recycling of spent nuclear fuel, but that's something that I think we'll see how the politics and things play out over in the United States. But it certainly can technically be done, safely done, and it's done in France. And you're about right that a very large percentage of the uranium in the spent fuel could be reused if the political landscape would support reprocessing.
Thank you. We have a lot of surface mines that are unused, but a problem of getting infrastructure to these places. Would it be possible to take one of these micro reactors and put there and automatically have the power source for these? Is that
Yes, that's exactly what the original intent. One of our first applications was remote mine sites that struggle with either diesel or literally are just too remote to be easily accessed at this time. It was one of our first applications.
Thank you, Mr. Lord. Thank you, Mr. Chairman.
Vice Chairman.
Thank you. My question was on so whenever you have unspent fuel in the micro reactor, and it has to be transported with the unspent fuel, but then it would be called nuclear waste, or a spent fuel would actually have to be transported. I know some states have talked about banning the transportation of nuclear waste, and that would create an issue on these would that create a big issue on these micro reactors where you're having to transport to a site to disassemble it and get rid of it?
Yeah, it certainly would depend, on the exact transit and things like that. But if all of the United States would not allow any movement of spent fuel, that would be a challenge. But this design is really made to have the spent fuel transport really be the same as the non-spent fuel transport. We're licensing this as a transport container, which Westinghouse has done for nuclear fuel that we ship all over the United States today. So, we would certainly look to avoid transit routes through states that would not allow movement of fuel. But we would expect that the potential of this technology, once you really look at the technical side of it, it's really not much of a difference whether it's spent or new fuel that's moving in this reactor.
And right now, do you have a site where you do store the fuel, or like if there was a reactor put in West Virginia and then at the end of that 8 years on those micro reactors, where would you assume that would go now?
Yeah, so, over this time frame, if we would decide, obviously working with the university, if they would support it as well, to embark upon this project, Westinghouse would begin also the process of either licensing a spent fuel storage facility or working with an existing nuclear utility to utilize their spent fuel storage, such that when we go to the NRC, you have to have a final location. You cannot cite a reactor in a situation where you don't know what would be done with it. It would be stopped by the regulator before it really even started.
Okay, thank you.
Mm-hmm.
Further questions? The minority leader.
Thank you, Mr. Chairman. Thank you for your presentation as well, too. Think of you when you move forward, the practicality of it from a production standpoint, like what does that mean? How much does it produce and what's the benefit?
Yeah, so from a production standpoint, we're actually working in Westinghouse of how much capital and where we're going to deploy capital to start, different parts of the supply chain for this machine. We're substantially using our existing supply chain today, but we see pretty large potential for these, so we're starting to look at how we're going to ramp up. As far as, what is really needed, over this time frame, we could start to qualify suppliers in West Virginia to substantially support. We already buy some of our special metal alloys from the state of West Virginia, and the team's actively looking at 2 suppliers in West Virginia to support this development. Does that kind of mean?
Yeah, and then when you do the development from a timeline standpoint, how long does it take, like start to finish?
Oh, to actually make one?
Yeah.
About a year.
About a year.
Yeah, certainly, we would have long lead materials and things like that already purchased. As you saw, many of them we have the capability to make now. The actual assembly, qualification, testing process would take about 1 year of that time then.
Thank you. Thank you, Mr. Chairman.
Gentleman from the 27th.
Thank you, Mr. Chairman. Thank you, sir, for being here today. Kind of a 2-part question. The first part is, you mentioned these micro reactors, approximately 5 megawatts. And how many households would that be possible?
Oh, great question. Typically, 800 to 1,000 households per megawatt is a standard number. The only reason I say that's standard, in far remote areas where electricity is being used for heating, it can dip as low as 300. But that's a good number, I think, for here.
And then the second part of the question is there a break-even period on the system itself? So, such as, okay, we purchased one of these microsystems right now. Does it pay for itself basically in 6 years, 8 years? Well, we hit the 8 years, now we've got to return the fuel and bring new fuel in. Is there a break-even point there?
Yeah, it depends on the application, but, for a university, it would substantially, would look at, what research could be done, third-party companies support using it at the university, things like that. Maybe a different economic model for a university than a typical, like a mine site, right? From a mine site perspective, it would be, they would look at what are their options, option A of perhaps diesel, option B of this type of unit. And then really the way to measure that especially over a long period of time is an analysis called levelized cost of electricity. So you basically figure out what is the financing, because nuclear is kind of more capital up front. What does that look like as compared to, another option, which tends to be more fuel cost and things like that throughout the life cycle. And you figure out what your overall cost per kilowatt hour, which one would be your better option.
Thank you. Thank you, Mr.
Gentlelady from the 35th.
Thank you, Mr. Chairman. Thanks, Mike. Can you talk about how much one of these microreactors costs? I know we know some large nuclear projects can be in the billions, but what are we talking about?
Yep. Yeah. So, first unit, we did an analysis where we put out a study in Canada we had a third party do it to look at what would our first unit be. And the range of capital costs there was in the ranges of around $90 to $120 million. The first unit, it's much smaller than obviously the billions of a very large nuclear plant, and the first unit of this will also be the highest cost. It's something that paradigm exists really outside of nuclear as well. You know, the first unit of a technology is always going to be the highest. We could see this coming down into the 60s to 90s over time, which when you translate that into a levelized cost of electricity, that's where the cost per kilowatt hour could be in the ranges of, 10 to 15 cents in the future. But in the early days, it's going to be probably in the 25 or so cents. But again, a university application, it's a different method of really the benefits and how you monetize it versus a pure electrical generation.
Mike, I might just ask, because I think maybe this group may be thinking about this question. So you use it for 8 years. You have to buy a new reactor. How does that work?
It's really just the refueling. So our intention is to, basically take the unit away back to a Westinghouse facility, similar, potentially even the same as our facility outside of Pittsburgh, where we would remove the fuel, put new fuel in, and allow it to be redeployed to another location or even the same location. So it's really the cost of that fuel and refurbishment versus an entire new reactor. Good question.
Are there further questions of the witness? Gentleman from the 10th.
Thank you, Mr. Chairman. In a university setting, what opportunities are there to recoup some of the investment by the state or the university?
Yeah, so certainly from even a cost perspective, these types of projects can generally garner federal funding interest in them to help offset those early costs. But then from a monetization of the reactor, U.S. universities today, they utilize private industry who's interested in using the reactor or testing things with it, perhaps even developing isotopes and things like that. And those entities come to the university and say, hey, I need time with this reactor. And there's a negotiation on time and cost and those types of things. As Westinghouse has been developing this technology, for instance, we're actually using the MIT research reactor up in Cambridge pretty frequently to irradiate materials, and we pay them for that time and that effort. And then other, benefits to the university, which is really then, supporting, that educational opportunity and things like that, which is maybe not direct funds going back into the university, but it's supporting really driving the human capital to do all the things that can be done in nuclear out of the state. Other ways could even be, supporting the campus heating, for instance, or supporting even electricity offset at the campus. So that's kind of why I mentioned a university application as far as commercial monetization of the reactor. It's very dynamic, and it's something we'd need to work with the university on.
Gentlelady from the 51st.
Thank you, Mr. Chair. Although most of my questions were asked by the gentleman who just questioned, but just to follow up on how universities might use this, can you tell us how many universities have units like this right now?
It's in the 30s. I wish I knew the exact number, but it's in the 30s of universities in the United States have them. And then there's certainly quite a few globally as well.
And how many have are Westinghouse units?
So most of the research reactors in the United States were actually designed and developed around in the 50s, and those were, Westinghouse was not developing research reactors at that time. So they're substantially designed by, I think, General Atomics and some others that were doing research reactors back in the 50s and 60s. But they're very old, and it's something that even the U.S. federal government has acknowledged. If we want to stay a leader in this space for both commercial and even defense, we need to revitalize the research reactor fleet that is, at this point, 60 to 70 years old.
And are there any, you mentioned that you have a unit in Pittsburgh. Are there any at the universities in Pittsburgh or anywhere in Pennsylvania?
No, so that unit is not the full-size operating unit. It was kind of one of the stepping stones to, get to where we'll build a full-size unit, operate that, around the turn of 2025 into 2026 at one of the U.S. national labs. That unit would be the first operating eVinci unit for which we would ensure it operates safely, et cetera, all the things that we, know that it will do, but we need to physically prove it in a final test. And then after that, we would seek NRC design certification and deploy it to universities or other locations.
Okay, thank you. Thank you, Mr. Chairman.
Gentleman from Mercer.
Thank you. And looking at the cost issue again, my memory is that 10 or 15 years ago, wind and solar were in the 25 to 28 cents a kilowatt hour range. Fossil fuels were in the 4 cent, so it's 7 times the expense. Now, wind and solar are down in the 16 or 18 range. So what you're describing is unit number 1 would start at about the same point in the development curve as wind and solar did. How far do you think you can go down that curve in a 10-year period, perhaps?
Yeah, I think that because there are some costs in nuclear that are somewhat fixed, regulatory and other things, we won't be able to achieve quite as steep of the cost curve as renewables. However, I do believe we can achieve, within that low 10 cents per kilowatt hour within really the first 5 or 6 years after the first unit's been delivered. There are huge economies of scale the way that we would make this in an automated factory versus how we're doing it right now, which is really kind of boutique manufacturing at our existing facilities.
Sorry, you're nodding your head. Does that mean those numbers, I was trying to confirm the numbers I quoted were realistic?
Yeah, I think you're pretty close on solar and wind. And honestly, we don't see ourselves competing with solar and wind with this technology either, just to mention that. We actually see this type of technology throughout many areas to actually support further deployment of renewables. Because of the intermittency in some of these remote areas, the grid just cannot deal with that.
Further questions? Senator Caputo.
Thank you, Mr. Chairman. One more. What is the cost of refueling these?
So the cost of refueling would be about 20 to 30% of the capital cost of the initial unit. And that's one of the areas where we're keeping that somewhat confidential at this time, because we know there's a lot of people our competition is trying to figure out how much the fuel costs.
Okay.
And we're quite familiar with the fuel side.
Thank you, Mr. Chairman.
Senator Smith.
Thank you, Mr. Chairman. Thank you for being here. So this is basically going to be targeting like manufacturing facilities, mining facilities, universities. Okay, all of them are big customers. I mean, they buy a lot of electricity off of the grid. How's this going, if we do this, how's this going to affect just your regular common, consumer, your ratepayers? Because as you take that off, they're still producing, so somebody's got to pay for it. So, have you looked into that? How's that going to affect just the, someone like us that just, how much is it going to increase the electric bills?
Yeah. So our intent is not to put these in locations that are going to increase people's electric bills, but actually put them in many, many locations where they would have an immediate decrease. Our early commercial market non-research would really be those remote communities, mine sites, potentially the Air Force Base in Alaska, where it's 30s, 40s, 50 cents per kilowatt hour, and some people being charged as much as $1. So our full intent is not to try to find ways to push this into the marketplace on consumers, but to actually bring it to the market and have an immediate positive impact on people's energy costs. That's really one of the reasons we embarked on this and why we're excited about it. It's not something we feel we have to force people to do. It's something that there's really a great need for in many of these areas.
All right, thank you, Mr. Chairman.
Delegate Krause.
Quick question. When you talk about refueling, how is that done? Does the grid that it's on have to shut down while you refuel, or is it a continuous?
Yeah, great question. So at a university application, you potentially would just shut the reactor off, take it away, and then bring a new one back into the exact same spot, because you might not be using it for the only source of energy that you have. But if we were at a mine site where it was the only source of energy, we would basically have one empty extra garage slot that we would bring a new unit in before the first one has become completely discharged. So we would have kind of that +1 slot capability, so you could keep continuous power generation at a site.
Thank you.
Great question. I should have mentioned it, actually.
A gentleman from the 10th.
Thank you, Mr. Chairman. when it comes to medical isotopes, how was this technology and that work together?
Yeah, so, let me scroll way back up. Just, it'll be easier to explain. So these rods are for, substantially only for transportation. Because as it was mentioned, we have to transport this, basically as a fueled reactor. So we need a lot of excess shutdown capability to be able to license this for transport. Those rods, though, there's huge redundancy once it's in its place of operation. And so we can remove several of those rods, opening up locations that we could slide isotope targets into the core of the reactor, such that we could do, like the university could do research on medical isotope with direct irradiation of specimens.
And that could potentially be a revenue source
Yeah.
for the university?
Medical isotopes is a huge opportunity right now, especially as a large percentage of medical isotopes come from Russia or did come from Russia prior to February 24th. There's actually a large scramble to utilize as many U.S. and Canadian nuclear plants to create isotopes as possible right now. And what, a reactor like this would do is not necessarily create massive volumes of isotopes, but allow researchers to look at different ways to efficiently make them and other different isotopes to be created such that you could find different applications for them.
Thank you, sir.
Senator Martin.
Thank you, Mr. Chairman. I just had a question on, are you looking more on targeting directly to the customers, or are you looking more to selling to like a power company?
I would say the end answer to that will be both. I think the technology is so much different than kind of the large nuclear power plant that is typically sold to a large nuclear utility. I think some of these will be sold to nuclear utilities. I think some of them will be sold to commercial utilities, and then some potentially directly to commercial users like a mine site without a nuclear utility in the future. But in the early days, our model is to plan to use kind of the typical model where Westinghouse is the vendor. We would have a nuclear utility operate it and then provide a power purchase or other energy agreement to the end user.
So for larger customers?
Yes. And then a university is a little different because their research reactors are licensed slightly differently with the US NRC, and they can be owned and operated by the university, with the US DOE owning the actual fuel in the reactor. So university is also a slightly different deployment model.
Further questions to the witness? I had one. Now, I've had the luxury of coming to Waltz Mill and seeing your site, and that's where you're going to be constructing these, going forward into the future. One of the questions that I had, because you brought it up a couple times, was about, West Virginia playing a role in that supply chain to build these with, the high-end stainless steel, the zinc, all the components going into that. As you develop this and you see that central location being around Waltz Mill, do you guys have a projection of what type of impact you would have, from a supply chain standpoint of needing West Virginia to step up, and how, if we had one of these at WVU, how could that bolster that?
Yeah, so maybe start with the last question. One of my examples that came to mind when we started at least thinking about this concept at the university is Carnegie Mellon University in Pittsburgh. They have a relatively small robotics program, but it's become really one of the best robotics programs in the United States. And then what happened to Pittsburgh was, once you're creating those engineers and those technicians and all those people through the university, we now have multiple pushing billion-dollar robotics companies that landed right next to the university, basically. So, has traditionally happened in nuclear. Early adopters of the technology, the infrastructure just naturally starts to build around them, because you start to build the human capital that's necessary. It's always convenient to have, a capable supplier or a group of suppliers that's very close in the region, because of how high of quality the manufacturing of these things has to be, right? When Westinghouse is buying something, we send engineers and people to go see it all, throughout its entire process. And having that regionally is just a huge, huge benefit. So, I think there's you know, there's a very clear path that's happened all over the world of where the plants are and where the central infrastructure is where the businesses that support it come around it. Waltz Mill, even though we're doing a lot of building and testing, and we may do some of the early builds or things like that at that facility, we haven't necessarily decided that will be where we do a scaled large facility yet. You know, there's things like that we'll still need to look at of, you know, the opportunity in different locations, you know, really, you know, what's the most economic way to make these in the future. Clearly in the United States, you know, because the technology will really reside in the United States and Canada. But even major portions of manufacturing could happen in West Virginia if the infrastructure starts to be planned for and readied now. You know, some of those decisions of where we're going to make, you know, we will do a kind of a garage manufacturing, maybe in Pennsylvania early, or maybe one of our other facilities. But then, you know, as we kind of get towards the end of the decade, if West Virginia is substantially ready, it could be an option in the future for larger and larger portions of the work. But certainly metals and many of the components of this, you know, Westinghouse partnering with suppliers here, we can make a lot of components now. And we are sending some of our folks down to a few suppliers, you know, really right now to get some West Virginia participation in the project.
Delegate Krause.
One last question. How much space do one of these require? And then how many employees does it take to run it once it's up and going?
About 1.5 acres maximum physical space. The building itself that was supported is about 60 feet by 60 feet. So from a footprint perspective, you know, rather small. And then from a pure operational perspective, really the technology requires zero, but we were working with the regulator, and obviously at a university setting, you know, one of the advantages would be to actually train people and have them work on the machine and do things like that. So, you know, around 4 to 5 people trained to work around the reactor would probably be an adequate number, but you would not need them all there all the time.
Thank you.
Are there further questions of the witness? Seeing none, I want to thank Mike. Thank you for being here today, and the rest of everyone at Westinghouse. It was very informative. I hope everybody got all their questions answered. That was the only item on our agenda today. So does anybody have any other business? Seeing none, I'll call on the co-chairman for a motion.
Mr. Chairman, I move we adjourn.
You've heard the gentleman's motion that we adjourn. All those in favor of the motion will signify by saying aye.
Aye.
All those opposed say nay. The ayes have it. We are adjourned. Thank you.